page 7, just to put you in the big picture. And at Booty Booty, we were just east of the main arc system there. So we were in the Four Arc Basin. We're probably around about halfway across it. The whole thing has been short because you saw those open folds within the Four Arc Basin there. And one of the points of coming here is to look at that bigger picture and contrast the structure that you see here. So we're not just contrasting the rock types, we're contrasting the structure. And if you look in the accretionary prism section there, what can you see happening? Faulting. There's a lot of faulting happening. What sort of orientation do you think the rocks are going to be in? Yeah, they're probably going to be pretty much vertical. What we saw in the Four Arc Basin is there was open folding, but they were folding about a largely horizontal bedding surface. What we see here, because you've got subduction accretion happening, is everything ends up on end. Now you can't see that here, but you'll see it as you go a little bit further up the beach. So I've got a few questions or sections to address here, and that starts on page 18. Now the Cherts and Jasper we'll look at a little bit further up. We often go down to the southern end of the beach, but there's a couple of reasons why we didn't go down there this afternoon. So what we're going to do is we're going to look at the basalt and dolerite questions first, over on page 21. And I'm going to go to question 4 first. Now what you're looking at in front of you is largely basaltic rocks. There's a few bits of chert lying around that you can see, but all this green stuff that I'm standing on and that you're sitting on is all basalt. Or I should say basaltic, because I'm jumping the first question there. We'll come back to that. And it asks you there what is the usual colour of the basaltic rocks, and why are these things green? Now again, I'd remind people not to look at weathered surfaces. I see students in the lab picking up rocks and saying, oh, it's orange on the outside. It's just weathering. You need to look past the weathering, you need to look at a fresh surface. Some of the orange there is in fact lichen, so don't look at that. The fresh surface of these rocks is a green colour. Now, this relates to another question that we're going to look at the first stop tomorrow morning, and you're asked there, why are black basalts black? Can anyone remember that? Yes, the pyroxene in them. So it's mostly the augite present, which is black enhanced specimen. Remember, they've also got a lot of plagioclase in them, but those minerals are transparent, so they just take on the colour of the pyroxene around them. So why do you think these basalts are green?
Olivine.
Someone said olivine. Well, green schist, that's a rock name, and it probably is at green schist facies in terms of the metamorphic grade. Probably lower green schist facies. But what I'm thinking at mineral level.
Olivine. Peridotite.
Probably not olivine. We'll see serpentinites further up the beach. These don't have serpentine minerals in them. So they're rocks that originally started out as pyroxene plagioclase rocks. They may or may not have had olivine in them, and they certainly don't now if they did originally. So what green minerals might be present? That's an element. That's an element as well. Someone said iron. They're all elements. Yeah, which type of amphibole? Because you looked at 2 amphiboles in the lab. One of them was hornblende and the other one was actinolite. Which one was green? Yeah, the actinolite's green. Hornblende's pretty much black, like pyroxene is. Okay, and you will get that at higher metamorphic grade. You'll get that at what they call upper amphibolite facies. This is below that, and so you get actinolite. Actinolite is a lower temperature amphibole, and it's green. What other minerals have you seen that are green in the lab? Olivine. Yeah, but there's no olivine in these. You saw it. Well, we inferred in the slate and the phyllite, I said there was a particular mineral making those rocks look green. Chlorite. Chlorite. Okay, so these rocks have probably got chlorite in them as well. Now we can't see this at hand specimen level because it's too fine grained. There's another green mineral that you haven't seen called epidote. It's E-P-I-D-O-T-E. That's green as well, and there's probably that in these rocks. So they're all at that temperature. They're probably sub 300 degrees. I'm sort of plucking a number out of the air there, but they're not high grade metamorphic, they're low grade. And they would probably have those three minerals in them. And they're all green. Okay, there would still be plagioclase in there. One of the other things we talked about in the lectures was seafloor metamorphism. And I said at the time, I probably threw the term spillite at you. Basalts, seafloor basalts get turned into things called spillites because they react with seawater. And one of the key things about spillites is that the plagioclase in them becomes very sodic. So it goes towards the albite end member. So that's the other thing that's happening to these since they formed that you can't see. But the green colour, which is what that question's about, are those three green minerals. Probably primarily actinolite and chlorite. Okay, we'll have a look at the structure over the other side here. But the other thing that asks you in question 3 there is what characteristics would allow you to distinguish basalt from dolerite? What's the difference there?
Grain size.
Grain size. Which one's which?
Dolerite's medium grain.
Yeah, dolerite will be coarser because they're usually sub-volcanic and they slow a little bit cooler and they're usually coarser grain. Do you think you'd be able to pick that difference once these basaltic rocks have been metamorphosed? That's a bit of a leading question, isn't it? There's the answer. No, you wouldn't. Why? What happens during metamorphism? Other than new minerals forming?
Recrystallization.
Recrystallization. So the whole thing's been recrystallised. So, on a first case basis, there's no way you'd be able to tell a basalt from a dolerite once they've been metamorphosed to this degree. Even though it's only low grade, it would be thoroughly recrystallised. What other ways might you be able to tell? Other than looking at the grains. What sort of structures do basalts form? Where have these formed in the first place, by the way? Where have these basalts come from? Seafloor. They're seafloor. What sort of basalts do you get on the seafloor?
Pillow lava.
Pillow lavas. So, you might expect, even though the rock's been recrystallised, you might expect, if they are basalts and they were pillows originally, you might expect potentially to see pillow structures still around. And there's possibly some over the other side here. Okay, but that would be the only way you tell. You can't tell by looking at the grain size or anything like that because it's all been, the whole lot's been recrystallised. Okay, and we've got looks like we've got a bit more sand here than we did last year, but there was a spectacular outcrop on the other side here of what's called a melange, which I think is described there somewhere.